Hi, hello, welcome to section 10. Um, so yes, I just said the thing about the exam scores. We have the practice finals, which you can pick up at the end of section, and um, the PDFs are going to be released this weekend, but as always, we recommend the paper ones. One nice thing, again, is all the studying that you just did for yesterday's exam is studying for the final. Any question that was on yesterday's exam could appear on the final. The final is not going to be harder. The final is going to have, I think, 2 or 3 questions that are mostly mechanism based, like lecture 10 questions. It'll have exam 2 like questions, and then it will have some questions from exam 1. So they're mostly separate problems. They could appear, like easy ones of the reactions could appear in like line reaction or synthesis, but we're not going to try to do something like crazy. It would have to be Ozzy.
He specifically said redundant reactions for synthesis.
So I have seen it appear in the past in the final exam once, but I'll tell you which reaction it is. I'll like go through and point out like she's appeared before. But the complicated ones where you have to do a lot of like weird disconnection connection, that's not going to be on any box problem or synthesis. Okay, so lecture 10, if we remember her from Tuesday, was all about enolate chemistry, about the alpha carbons. So we're going to talk about forming enolates. We're going to talk about the big boys, the aldol and the claisen. And then we will talk about the kind of details and miscellaneous things, odds and ends. Any like logistic questions before we jump into things? I'm going to get my little soundboard up. Oh, I have new transitions for today. For the last section, I found some that I wanted to try out. Okay. Let's dive in, I guess.
This is my meal. I call this girl dinner. Girl dinner. Girl dinner.
Enolate chemistry. My girl dinner. So, to help us with lecture 10, because like there is a lot that looks very similar with it, I've kind of split it into like 6 or 7 big ideas that kind of group the whole lecture. So the first big idea, the most basic one, is that hydrogens at an alpha carbon are acidic. So we know that if we have a carbonyl, we label the carbons to the left and right of the carbonyl, the alpha carbons. And the pK of those hydrogens are around 20, whereas the pK of an alkane is about 50. So if it's slightly more acidic, what we can do is deprotonate it with a base. And because of resonance, we get this structure called an enolate. The enolate is like an O minus combined with an alkene, so ene and then 8 as in like, 8 is typically an ending that's associated with esters, but don't worry about it. But there is like an MO requirement, just like for E2, like beta hydrogens being antiperiplanar. And that's that we need our sigma CH at the alpha position to line up with the pi star CO, so that when we deprotonate it with a base, the electrons can just slide into that antibonding orbital and then go over to the oxygen. So again, alpha hydrogens are acidic. The second big idea is enolates then are nucleophilic at the alpha carbon. So what we can do is push down and have the double bond in our enolate go and attack some electrophile, and suddenly we've just made a new carbon-carbon bond. Very powerful. For exam 2, you only knew 4 ways. This is now a big, big 5th way that has a lot more opportunities with it. One note, just kind of like the alcohols versus alkoxides, is the enolates versus enols. So enolate is when it's negatively charged. Enol is when it's neutral. And an enol is also a nucleophile. It can also do these attacks to some electrophile, but it is not as strong of a nucleophile. So you can do this chemistry either in basic conditions where you'll be working with enolates or acid conditions where you'll be working with enols. Enols are tautomers, of ketones, which tautology just means like equal. So they have the same molecular formula here, RC2H3O. but they have just arranged the atoms different ways. Another way of thinking about tautomers is they're just a special kind of structural isomer. So we can either in base or acid tautomerize our ketone to an enol. So in acid, our first step is always protonate the carbonyl. Then water would be our base that would just deprotonate the alpha position, and then we are at our enol. Or in base, we can just have the OH minus directly grab the hydrogen, and then we can neutralize the O minus. So getting between these two is kind of a classic, like, baby steps mechanism into the space. And then I think I have, where is it? I'm missing one of my sounds. Give me 1 second. There she is. So we have a lot of different flavors of enolates, and so when we see all of them, it's very like choose your fighter, all of the different enolates. We have our classic ones from aldehydes or ketones. Their pKs are more neutral, around 17 or 20. Then we have enolates that are from esters as well, which is slightly worse, but not very. And then we have the dicarbonyls. So if we have an alpha position that's between 2 carbonyls, it is suddenly much more acidic. It's more like 11 or 13. So it's more acidic than just a normal alcohol. Then, generally speaking here, when you have the choice of 2 things to go on, like here, a ketone or an ester, you're always going to want to go towards the non-ester, I guess. So you're going to want to go to whoever has less electrons around it. You see how this ester already has electrons feeding in from this OR on the side? So that is why when we are deciding what do we do with the electrons in this bond, well, this one already has some stuff going on. So we are going to fold it in over this way towards the ketone. Is also why, like, the aldehyde is more acidic than the ketone. It's because this R group is slightly donating via hyperconjugation, and so it's going to be less acidic there. It's going to be less want to, when we deprotonate this, have the electrons fold in. Weird ones include nitrile. So this is technically the alpha position of a nitrile, and what you can do is you can deprotonate it, push in, and then this CN triple bond you make into a double bond like this. It looks weird, but it functions the exact same way. This can push down, and this double bond can go and attack something at the alpha position. Enamines also fall into this camp, where you could push down from the nitrogen, and this could go and attack something at the alpha position. So let's see this in practice. So the first one here is challenge problem 4b. What do you think our nucleophile is? Is it one of our fighters up here that we said was a good nucleophile at the alpha position? Enamine, thank you, thank you. So our enamine, we know that we can go and push down, and this double bond can go and attack something. And in this other molecule, we have a couple of different electrophile sites, right? So what's one electrophilic site? Yeah, we have the pi star, or we have the sigma star. And based on our product over here, does it look like we attack the pi star or the sigma star? Sigma star. So this double bond will go and do like an SN2 like backside attack here. Then we will get to a structure where it's also like very, very easy to add or subtract a carbon when doing these mechanisms. So I like using little stars to help keep me on track. So if this red star was the one that we attacked, and this yellow star was the one that did the attacking, then we have one more and a hydrogen. We've made a double bond with our nitrogen. So it's now this aminium. And then from here, the rest of this is just amine hydrolysis. Electrophi mechanism that I think you all know by heart now after the exam. So easy. So that's another like theme of this lecture is it's one new thing, and then we also are kind of mixing in some old chemistry that you've seen now. Then we have, this is challenge problem 1, talking through some of the pKs. So what we have is these two bridge structures, bridge rings, and both of them are carbonyls, but one of them has a pK of around 20, and one has a pK of around 40. Which one is closer to what we would expect for an alpha hydrogen? 20, yeah. Like we said that ketones, aldehydes were like, yeah, ketone classically, 20. So this one does normal alpha hydrogen deprotonation. This one's more similar to an alkane. So what gives? Like, why can we have an acidic hydrogen on the left and not one on the right? Any ideas? It seems to be related to where the carbonyl is placed.
Is it that idea of the building, like you have to have sigma CH bond next to the pi star?
Ding dong. Remember I said there was an MO requirement? And just like MO requirements with E2 on a ring, here, when we are on this bridged ring, we can't rotate freely to just access this. So we have to make sure we have a hydrogen that could overlap with the pi star. So for both of these, I'm going to draw the pi star. And then I'm going to draw out all of the alpha hydrogens, sorry. So this one, we'll have one that's kind of down, we'll have one that's kind of up, and then we'll have one that's out. And over here, both of ours are going to be out. So, 1, 2, or 3, which do you think is going to line up with the pi star CO? And maybe I should say line up best with the pi star CO. Well, 2 is going to be kind of perpendicular because these are like up and down, and this is left and right. So if we want it to be parallel to lined up, which one looks most parallel? 3. So what we're going to have is this beta hydrogen, and I'm going to erase the other hydrogen just to make it a little bit clearer. It is going to be able to overlap into this. Part of it is like how I drew it was not the best drawing, but there we are. So our base is going to come along and then fold the electrons in and up. And so we are going to be able to get this enolate. Now, why could we not do this one? We already said that the hydrogen wasn't aligned, but let's say it could like bend itself. Why is this not a good structure?
You have a double bond at the bridge head.
Yeah, it violates Brett's rule. So, like, you are just not going to be able geometrically to get that to happen. Okay, so this one works. And then it seems, obviously, with the pK being 40, that we're not going to have a good overlap over here. We're not going to be able to do it. And the way to think about this is here, imagine these are left and right in the plane. This hydrogen is coming out towards you. So it's like almost perpendicular to the pi bond, so there's no overlap here. And then also it would violate Brett's rule, so a double whammy. So over here we had the sigma CH donating to the pi star CO. Here, no sigma CH overlap with pi star CO. And then just to draw it so we see how horrible, rotten, disgusting it is. We do not get this structure because it violates Brett's rule. And then the second part of it follows it up with these two carbonyls on just a chair structure. And who do we have on the chair that's kind of locking the situation down? Tert-butyl. So we can't do a ring flip or anything. Let's again draw in our pi star. Bloop, bloop. And then let's draw in our alpha hydrogens. We have 1, 2. Between option 1 and option 2, which one can line up with our pi star? 1. 1 is a lot more aligned over here. And again, the angle might be a little bit off. It's not going to be as strict of a requirement as the anti-periplanar, where it has to literally be 180. But it has to be enough to where this thing could wiggle just a little bit and it would line up. And so here, this one is more closely aligned with this, whereas this hydrogen is like down to the side, and so it's going to be almost perpendicular. This type of looking for like the stereochemistry of, or I shouldn't say stereochemistry, like the 3D, like MO requirements, it comes back a lot in 27, and again, they'll train you more explicitly on that, but I think it's good to like flag now as something that, hey, this is going to come back. So now when we do this, our base is going to be OD minus, like OH minus, and what we get is our chair, where now we have formed this enolate. And here. And what we see in its place is a deuterium has been added. So all we did is we removed a hydrogen here by making an enolate. And now our enolate's just going to go down and grab a deuterium. So it's kind of a silly mechanism, like we're doing something and then undoing it. But the purpose is to show that, hey, the only side we're going to form an enolate on is this left side. If we were forming an enolate on the other side, then we would have some product that would have a deuterium here, and we don't. So thoughts on these kind of initial ideas of enolates as nucleophiles of the alpha carbon, and then also this like MO requirement of the alpha hydrogen and the carbonyl. I'm gonna get out my little drink. I know. Yes.
Why is it that specific MO overlap allows us to have that?
So it's because of the bonds that you are breaking. Like when you deprotonate the alpha hydrogen, the electrons in this sigma bond have to go somewhere, right? And we want it to do resonance, because otherwise, if we do not do resonance, then we have a negative charge on a carbon, which is not good. Like that's the pK of about 50. What allows this to be acceptable is if the electrons here can flow into the pi bond, it's making resonance happen. Like right now, this is an sp3 hybridized carbon, but then once you deprotonate it, it all becomes sp2, right? Because there's resonance with the 3 atoms. Yeah. Mm-hmm.
Are we mostly just gonna have to worry about it for rings?
Yeah, like I honestly don't think you're gonna have to worry about it. I just wanted to knock out those PSEC questions because they're weird. Like I don't think we would ever ask you about this. And for like the rest of the class or the rest of the section, I'm not gonna mention it again. But it was just like this is our pit stop. All aboard MO station. Cool. Any other questions about the basics? I'll keep on chucking. So, our third big idea brings us to an icon and a legend, the aldol reaction. So the fundamental idea behind the aldol reaction is enolates can attack ketones and aldehydes. So our nucleophile is our enolate, and our electrophile is a ketone and or aldehyde. Now, when we do this, there is technically kind of 2 forms of the aldol addition and the aldol condensation. And the addition is kind of an intermediate product that you can stop at or it can drive all the way to the condensation product. In order to figure out which happened, we need to think about new functional groups that we are like on the lookout for. The functional groups will be your key to the lecture 10 questions on the exam to figure out what happened and why. So the ones that we are looking for in the aldol, for the aldol condensation all the way at the very end, we have an alpha beta unsaturated ketone, which you guys know better by what name? Enone. And does it make sense? Alpha beta is where the double bond is. Unsaturated, like unsaturated fats, it has a double bond. Carbonyl. That's her technical name, her government name. You've known her by her like given name. Or wait, no, given name is chosen name. Yeah, her chosen name is Enone, but her family calls her alpha beta unsaturated carbonyl. It's a point of contention at Thanksgiving. So this gives us the condensation product. And then our aldol addition product is a beta hydroxycarbonyl. So we go alpha beta here, and we see an OH. And this is called an aldol typically. And it's particularly an aldol when there's a hydrogen there, but we kind of call whatever, like beta hydroxycarbonyls, aldols. And again, this is a stable intermediate and stopping point. And you can see if we go on further, we're kicking off an OH, and technically we're kicking off another H over here. And so using the biologist version of chemistry, what did we kick off? Water. So condensation. Biologists. They understand a few things. Yes. So let's talk through it just a little bit. First off, we are in basic conditions. So our reagent that we use is some base. We can use OH minus, and we'll talk about some other bases later. It's going to deprotonate the alpha position. Great, we've seen it. And then we have the key thing to be an aldol reaction. The enolate is going to go and attack the carbonyl. Now, when you attack it, you're making a carbon-carbon bond between this red and the blue highlight. So tracing that over here in the product, we now have the blue highlight connected to the red highlight. We've reformed the carbonyl on the red side. We've added our R2. We still have that hydrogen that was on the aldehyde over here, but we're just not writing her out because we can imply her. And then we have a negative charge. Let's neutralize it really quick, and we're already halfway there. The aldol addition product. There she is. But again, we are still in base. And so what can happen is the OH can go and deprotonate the alpha position yet again. And then we can do the super lone pair push, which, what was Logan called? The deluxe. Okay. Luxury. Yeah. It's not giving luxe to me. It's giving, like, going to the pool and, like, there's a little kid that's, like, trying to, like, water bend and go, like, that's the energy of it to me. And so I don't really view her as deluxe, but I do view her as super. She's definitely trying to have some powers. So this is the super or deluxe lone pair push. And her technical name is the E1CB mechanism. So this name comes from the fact that we formed a double bond, right? So what type of reaction? Elimination, E. And it's kind of, the one is, its rate depends only on one molecule. And CB stands for conjugate base. So we formed the conjugate base of this molecule over here, and then it pushes off, and it does it all on its own for the slow step. So that's E1CB. There's no, like, carbocation, which you're normally used to seeing for E1, but, yeah. Work. And that's how we get the condensation. Now, if we want to kind of select for one or the other, one way that some classes do to, like, notate that we specifically want the condensation is they put heat with the base, and that heat drives it all the way to the condensation. For us, I don't think that we're picky. Like, typically, especially for mechanisms, we'll give you the product, so you should be able to, like, see where it stopped. But, yeah, in case you see it in the future. Let's try out challenge problem 7. We're not going to do all of it, but we'll start it and talk about some of the tricky things. Do you want... Actually, I'm going to give you three or 4 minutes to just do it, because this is like a straight up, step 1 at least, is going to be a straight up aldol reaction. And don't do step 2 yet. So I want you to do the full aldol condensation mechanism and wind up with an enone. as your product. And then we will talk through step 2 together. Oh no. So were you able to decode this question? That was the name of the song that was playing, Decode by Paramore, so that was a pun. Yeah. How'd you do? Were there any steps where someone did something different? Like, did anyone go and deprotonate and make their enolate with the bottom? That's totally fine. It's symmetric, so it doesn't matter. So we make our enolate. Enolate goes and attacks. Then we neutralize it, and we are at our aldol addition product where we have our OH here. Then it's going to keep on reacting, and we deprotonate it, make our enolate again, and then we do our super lone pair push and water bend off the OH. So what we get at the end of the day is our aldol condensation product, the enone. And then step 2 says use NaBH3CN, ETOH, and heat. And this is a variant of NaBH4, and it's a variant that only adds 1,4. So like earlier in the course we said that there's a variant of sodium borhydride that only adds 1,2. And what did we have to sprinkle in to do that?
Sodium chloride.
Yeah, to make CeCl3, and that's our Loosh reduction to only do 1,2. This is a way of only doing 1,4. This is not going to be like on exams or something, but just the more you know. So all we do is HBH2CN. This is going to do a 1,4 attack. And we push up our enone. And then finally, last step, the final like follow-up to conjugate addition, is we just do an alpha protonation in order to get our carbonyl reformed. Ding dong. So is that 2 whole challenge problems done already? Well, so glad we came to this section. Let's talk about yet another challenge problem. Or are there any questions on this one? Yeah, this one should be more straightforward of like baby's first aldol reaction, and then we add in the second step. Now, challenge problem 2A. First up, we have a Grignard. The Grignard could attack the carbonyl. What else could it do? She's a base. She's a base. So what we are going to have is our Grignard, PHMGBr, is going to grab a hydrogen and make an enolate. Bless you. But then, what is she going to attack? Because all we have in the mixture is our starting molecule and more Grignard, and Grignard's not going to be an electrophile. Ding dong. So if we label these 3 carbons on our starting molecule here, we have it there, and we have another equivalent here. So we have 2 equivalents of it. Also, we can see that when our benzene ring grabbed a hydrogen, on the benzene ring, we just added an H. And so this is just straight up benzene. So we have made this product. It was just kind of a side product that fell off when we protonated the Grignard. But now we are going to have another equivalent come along, and we are going to do an attack. So 1 equivalents are a nucleophile, 1 equivalents are electrophile. And now here's the weird part. So normally after this, you would get a hydrogen from like water. But because we are in a Grignard, we don't have water, right? So this is the step actually where we have to move to step 2, which is acid workup. So we're going to do H+. We are now in step 2. And now it's a little bit different getting to the end because we are in acid. So in acid, all of our protonation states change, but we're doing the same things. So like what we did in base at this point was in base, we deprotonated this hydrogen. We're not going to be able to deprotonate that right away. So what we do in acid is we first protonate our H+, and then we can go and pull off our alpha hydrogen. And this is just going to be by something in the solution. And so now, instead of an enolate, what have we formed? We formed an enol. And normally at this point I would just be like, you can finish the rest on your own, but do you want to do the rest of it together just to like knock out more things? Or do you want to see like, yeah, I mean we're so close. So again, we're doing the same kind of goals, but we're in acid. So before we made our enolate, and when we made our enolate, we did our super lone pair push and we kicked off OH. How do we think that's going to change in acid? Well, we've made our enol version, but do you think in acid that we can push off OH minus?
Push off water.
Yeah. So we can't push off OH minus in acid, so we need to protonate our OH, make it a good leaving group. And then we can do our super lone pair push. Wow, it's gotten cramped up in here. Up in where? Up in here. It's more likely than you think. So, we would push down, push over, and kick off. And we would be so close to the product. Gosh. And then we just would have a last step of, right now, our carbonyl is protonated, and we would just want to deprotonate it. So same exact like setup premise, but just different protonation states. And so just flagging again that this is in acid. I'll put need H2O leaving group. Yeah.
Other than the product, is there anything that from the beginning that tells us we're not doing Grignard?
Yeah, so what would you expect for a Grignard?
Like, it to attack.
Yeah, and then your product would be like an alcohol, and then you've added, like, we can draw that product. We're experts at it. So, I mean, if you did not see this, then we want you to do enolate chemistry. This is going to be formed in some amount. Yeah. To be honest, like, that's probably the major product, and this is probably the minor product. But here we are. Cool. So let's talk about, for big idea number 4, our like classic aldol reaction is a molecule attacking another copy of the exact same molecule itself. But we can do a lot of variants of this, and we can see the whole aldol diaspora here, where aldol can attack other things. Like, we want the only thing that makes it an aldol reaction is attacking a ketone, or an aldehyde is our electrophile. But the exact identities can be different. And so this is something I haven't seen commented upon in like any other textbooks. So maybe I discovered it. But no one really talks about the cha-cha slide concordance of the aldol family reactions. So the classic aldol is exactly what you would expect from the cha-cha slide. It's
Slide to the left. Slide to the right.
they're the same molecule. They're attacking themselves. Our crossed aldol is when one molecule becomes your enolate and it attacks a different ketone or aldehyde. And does anyone know what that would be in the cha-cha slide concordance?
Crisscross. Crisscross.
Exactly. Then we have the intramolecular aldol. So, like our carbonyl, like enolate, is going to be on the same molecule as our electrophile. And this one has two parts to the cha-cha slide concordance, which I think is just fun. So one is,
Last time to get funky.
and then the other one is,
Cha-cha real smooth.
and it's kind of doing a little dance and folds into a ring. And then finally, we can do the retroaldol. So this is a completely reversible reaction. And so we can drive the reaction the other way. And we're going to talk a little bit more about the retroaldol in a minute. But this is indeed...
Reverse. Reverse.
And then there's also Take It Back Now, y'all. But I don't think I have that on the soundboard. But then to kick off the cha-cha slide, can we do the claps?
Freeze. Everybody clap your hands. Come on, y'all.
Again, if you had an interactive audio clip in an Orgo textbook and it talked about the cha-cha slide concordance, would it make you be like, huh?
Yeah.
I think I write a PhD about this actually.
Wow, thank you. Thank you. Again, understudied, underfunded. So, again, all of this, same exact reaction, same arrows, but just a different interaction between the two molecules of our nucleophile and electrophile. The retroaldol, I'm not going to go beat by beat through it, but it is exactly the reverse. It is exactly undoing it. So just like you learned the imine reaction forward and backwards for lecture 5, learn the aldol forward and backwards, and we are going to more heavily expect you to be thinking backwards with these reactions as well. So the retro reactions are going to be important. So like the last thing that we did in the formation was we kicked off an OH with our super lone pair push. First thing we do here is we add it 1,4. Then before that, we made an enolate. Now we need to unmake our enolate. It's beat for beat reverse. The bigger skill, I think, is actually going to be doing disconnections. So the disconnection skill you've seen now before each of the exams is going to be like a critical thing to working the problems. It's going to be critical even for the lecture 10 stuff, even for mechanisms, because we'll ask you to do things that are a little bit more complicated. Like we might ask you to do a retroaldol followed by a claisen or something. And just being able to draw what that intermediate goal is of the retroaldol is really, really helpful. So, how to spot an aldol. You are looking either for the beta hydroxy to a carbonyl, or you're looking for an enone. Let's do it together. So, in our first molecule, we see our enone. We see our alpha and beta position of our alpha beta unsaturated carbonyl. And the key to breaking it is you know that the alpha carbon did the attack, right? So when we break, we are going to break between the alpha and beta position. Now the alpha side was the nucleophile. So on that side, we will have our enolate. So that is this girl over here. And then on our right side, that was our electrophile. So we need to make it a carbonyl. Then we can go back even further if we want and get our carbonyl version of our enolate. And what do you notice about these two? They're the same thing. So we had a classic aldol. So that is going to be the kind of process. So find either your aldol or your alpha beta unsaturated, that's what I mean. you're going to break between the alpha and beta. On the alpha side, make it into the enolate. On the beta side, make it into the carbonyl. So, do you want to try the second one on your own? Like 30 seconds? Bless you. And I'll also try the third one as well. Okay. So in our middle one here, we see our beta hydroxycarbonyl or aldol. We can label our alpha, beta positions, and we know we're going to cut between them because our alpha carbon did the attack. So on the alpha carbon side, that's the side that was our enolate. And then our beta carbon side was our carbonyl. And here we have a hydrogen present, so this was an aldehyde. And again, we can go back one further and just turn our enolate all the way back into our carbonyl. And with that, we have this. How'd you do? And then where are we disconnecting in this third one? Is this an enone? No, that's sp3. Is this an aldol? That's an alpha hydroxy, not a beta hydroxy. So do you know what this is? This is a trick question. Oh my gosh, how goofy. Really silly goofy. So again, being able to spot these is really important. It's like half the battle to not waste your time on the exam. Now, one thing I do want to look at with another one of the challenge problems is the idea of this retroaldol. So look at our starting material here. Do we have an aldol addition product or aldol condensation product in our starting material? Do you have an aldol or an enol? Enone, sorry. We have an aldol, right? So is this the aldol addition or condensation? Addition. So this is our alpha, this is our beta. And what do we have in our product over here? We have the enone, which is our condensation. But does it look like this double bond? Like it seems like going from aldol addition to condensation, normally all we would do is just make a double bond, but that is clearly not the product that we had. So something different happened. So aldol addition, we know it could go on and do the condensation where we have a double bond right here, but it can also go backwards. So let's try our disconnection with this aldol and try to redraw what it was before the reaction happened. Like do the same disconnection that you just did above. We cut at the alpha beta position. On the alpha side, we have an enolate. And then on the beta side, we have a carbonyl. Well, let's go back one step further even. So here we did the retro aldol. Let's get it all the way to the carbonyl version. 2, 3. And I'm just kind of writing it out as a straight chain. Well, once we are here, we know that we have to do like an aldol condensation, right? But if we look at our enolates, this is symmetric molecule, so we either have the green version or we have the purple version. If we do the green version, then we go to this enolate and then we go to this product, right? So it would go backwards to what we had just done. But if we make the purple enolate, so if we go and deprotonate this, then let's count some carbons. We know our alpha carbon is going to be 1. It's going to connect over here, 2, 3, 4, 5, 6. So we know when we push down and attack, it's going to make a 6-membered ring, which I'll make that a better arrow. And hey, that's going to be what we want to get to our product here. So we have not done the full thing, but we've sketched in enough of the kind of intermediate details that then, if you especially are looking at the mechanism for the aldol by retroaldol, you'll be able to kind of fill it in from there. But do you see how this disconnection was a really important skill in order for us to be able to do that and just figure out what's going on? I love this problem. Bless you, all the allergies. So 3A is like this, 3B is also like this for Claisen, and we'll talk about it a little bit. But these problems are beautiful. Like, they are beautiful for getting you to work forward and backwards with the aldol and get really comfortable with them. But I can't help but think about this as the Rasputin dance from Dance Dance Revolution. Does anyone know what I'm talking about? The Rasputin, and in the dance, he like pops down, pops up, pops down, pops up, and like this is like one version, and then this pop down is like, ooh, on my straight chain, which enolate will I become? And then it pops up and becomes a different version, and so it's no, cool. I think that's all I have on aldol. It's so sad. Such beautiful chemistry. Any questions? So just as a recap, the aldol reaction is characterized by what as the electrophile? What are we attacking? Functional group wise. Ketone or aldehyde. Great. So the Claisen reaction said that's fine and good. What if we attack an ester? So in our Claisen reaction, we have an enolate as our nucleophile. We have an ester as our electrophile now. And what we get as our product is a beta dicarbonyl. So this is, the technical name could be something like an beta ketoester. But generally we just want 2 carbonyls and we want the relationship between them to be alpha and beta. Why is this different? Well, when we go through this, everything is starting out the same. We make our enolate attacks, but then, hold on. On this step, when we just attack like a ketone or aldehyde, these are carbons. Nothing can leave. So all we can do is like protonate the O and then try to make a better leaving group, kick it off. But when we attack an ester, she has a leaving group. So we can do a lone pair push, kick off our leaving group. And we've made our dicarbonyl. Now at this point on the test, you'll be like, easy question, done. Oh my gosh, I'm so glad. I'm so glad. But we've just made a dicarbonyl. And didn't we say dicarbonyls were more acidic? than normal carbonyls for the alpha hydrogens. Like over here, dicarbonyl is around 11 or 13. Initially, we had deprotonated something around 17 or 20. So if we're still in that mixture with the base that's strong enough to deprotonate this, is it going to deprotonate the pK of 11 one that we just made? So this is what I call the annoying step. So in the annoying step, what you do is you deprotonate this because it's acidic, you push up, and then you move on to step 2, which is an acid workup, and you completely undo it in the next step. And then you can be done. And it's annoying. But not doing this will be -3 points on the exam. And I know this because when I was learning these reactions in OChem 2, do you want to know what I forgot to do? The annoying step. And do you know how many points I lost? 3 points. So it's a thing. It's coming for you. Know that she's there. It's kind of like the It Follows like monster that like moves very slowly, but like is out to get you. So just like know that she's following and be like, okay, I guess I'll do the annoying stuff now. But to give you like a couple of minutes to try this out, actually I think I'll do it with you to save some time. So we have our starting molecule over here. We have Naomi. We start off by deprotonating at the alpha position, and we could do either one because it's symmetric. So push in, push up. And then our enolate is going to go and attack our ester. So again, Claisen is enolate attacking an ester, whereas aldol is enolate attacking a ketone or aldehyde. So when we do that, we're making a 1, 2, 3, 4, 5-membered ring. Beautiful. That's what we want. I'll number 1, 2, 3, 4, 5. So carbon, no, I'll do it the other one. 2, 3, 4, 5. So in carbon 1, we've reformed our carbonyl. 2 is boring, 3, 4 is boring, 5 is not boring. 5 has an O- and an OMe. And so, because we have a good leaving group, and we have this tetrahedral intermediate, we can push down, kick off OMe. We're done. We have our product. Moving on. Oh no, what did we forget? Again, if you had just done an arrow here to the end, -3, it follows. It's going to get you. So we have to do the annoying step. So we formed a dicarbonyl. We are in base. Another equivalent of OMe is going to go and grab the hydrogen. And then now, do we push towards the ketone or the ester? The ketone, because it's less electron rich. So, Mio. Also, every time I say Mio, I think, me, oh my, fun. What is that? It's some song. I don't know. Now we are at our enolate, and then we directly undo it. And we can also just hashtag it annoying, just so everyone knows what's going on. Here we are. Yes. And then 3B, we're not going to work through it, but it's the exact same idea with the Rasputin dance thing that we did before of we're going to do a retro Claisen. We'll get to a straight chain. And then we will do a different Claisen. So it'll be some practice with the same kind of skills there. Any questions on the basic Claisen reaction now? The Claisen similarly has a Claisen diaspora with a Cha-Cha slide concordance that I didn't write out just because it takes time, but same categories. So it could attack another copy of the same molecule. It could attack a different ester. Another way that we can have across Claisen is our enolate nucleophile doesn't have to be from an ester. Like, even if we make like a ketone or aldehyde enolate, if that attacks the ester, it is a Claisen reaction, because the whole identity of the reaction is determined by what our electrophile is, what we attack. Because when we attack an ester, we have a leaving group. When we attack a ketone or aldehyde, we have no leaving group. And so that is the like crux of it. Retroclaisen, we're working backwards to the same thing. Let's try our disconnection practice here. So the disconnection practice is a little bit trickier with the Claisen. So I'm going to start off with, I think, the middle example. I'm going to do it with you. So the product functional group that we are looking to spot for a Claisen is a beta dicarbonyl. Do we have a beta dicarbonyl? Yes, we do indeed. So there are two ways that we could number it. We could do alpha beta, like this in red, or we could do alpha beta, like this in blue. And the important part here is whatever we call our alpha side, alpha is going to be the nucleophile. Okay. So if we have the choice between a ketone on one side and an ester on the other side in our product, which do you think was the nucleophile and which was the electrophile? Any ideas? The ketone was the nucleophile. So you are thinking that it is, we cut this, oh, wait, ketone is the nucleophile. What am I doing? Yeah, sorry. So that would be cutting here, right? The ketone is the nucleophile. So that would make the alpha side the enolate. And then we have our O down here. And then, ooh, well, our electrophile needs to be an ester. It would be something like this. That looks kind of weird, right? We've never seen carbonyl with oxygens on both sides. She's actually a different reactivity than anything you've seen before. She's going to be at the carbonic acid or like CO2 level of reactivity. She's no longer a CAD. So like, while I like the instinct of like, oh, okay, our ketone is the nucleophile, when we think about it, the Claisen reaction, when we attack our ester, the OR group of the ester leaves. So in the product, whatever our electrophile is, was a ketone or aldehyde here. So we could do this way of disconnecting, and that's going to be the red method. Or we could do it this way. And if we do it this way, then what we get is the enolate at the bottom over here, and the top, we have our ester electrophile. And this is our nucleophile that was also from an ester. So here, when there's a choice between an ester and a ketone, it's easier to see which side was the nucleophile. The nucleophile was the side that still has its OR. And maybe I'll make this a different color. I'll make it green. But now, for this one, it could be either way, right? Like, neither one of them has an OR group. So we're just going to get two options. So we get one option where we do alpha beta this way and we cut. And that option, we have this enolate with this ester. So the beta side becomes an ester electrophile. Or we can number it alpha beta and disconnect over here. In this version, on the alpha side is our enolate, and then on the beta side is where we want our ester. And I've just done OME for all of these, but you could do any OR. So both of these combinations would work. Questions about her? She's a little bit harder of a disconnection than aldol. Fundamentally, though, you're still cutting along the alpha-beta bond. It's just unclear which way you want to count it. And then, do we have any Claisen disconnections in this molecule? Oh, shoot. Ah! What are you doing? In her. Now we have alpha dicarbonyls. We have alpha hydroxy. We do have an aldol. We could do something, but we don't have a clase, and so, do you know what this is? Ah, silly goofy. Silly and goofy. Work. So that's kind of basics of the Claisen reaction. You're going to get more practice with it, and again, I would just recommend kind of working these reactions forward and backwards over and over until especially the aldol and Claisen feel really comfortable, because the type of mechanisms that you'll see for these on exams are going to do transformations that involve rings, involve things that look weird, and so half the battle is just recognizing what's going on. But with that, I will transition. So y'all are now enolate experts. We have 2 carbonyls here. We're adding a base. Which of these products are we going to form? I'll give you a minute to think. So what do our contestants think? Does anyone want to put in an answer? Which do you think form, or which do you think do not form? All of them. You want to lock that in, Ozzy? Yeah. So, if we made our enolate on the left of our red and orange one, we could attack either another equivalent of the orange and get product A, or we could attack the green and blue one and get product B. Then we could also make the enolate on the right for this one and get 2 more products. And then we could do the green and blue enolate on the left or on the right, and we're going to get different products every time. So if we have the option of forming 1, 2, 3, 4, 5, 6, 7, 8 products every time we're trying to do an aldol Claisen, does this feel synthetically useful? No. So our big idea number 6, we can limit the multitude of potential products through symmetry, lack of an alpha hydrogen, ring size, and sequential addition. So symmetry is just one way that you can cut the number of reactions that you have happening is if it's just the same on both sides, then there aren't 2 choices of enolates. So that is one nice way to do it. Then we also have one-sidedness. So if we put on one side something that doesn't have an alpha hydrogen, so like an OME, a benzene ring, a tert-butyl, if we make an aldehyde, that's not an alpha hydrogen, and then here, whatever this is, none of these have alpha hydrogens on both sides. They only have one option, and so we know for all of these, the enolate's going to be formed at only one site. So another way of controlling the chaos. We truly also can use molecules where we have no-goes on both sides. So in a reaction, these where we have the no-goes on both sides have to be the electrophile. So they could not be a nucleophile And so spotting, like especially when you're trying to see what's going on in a reaction, spotting what can even be the nucleophile is important. For ring size, we can do things like, well, we could form this outside one, or we can form the inside enolate. Those are kind of our two options. But if we do our outside, we'd form a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. So this is the outside one. And if we do the inside one, we'd form a 1, 2, 3, 4, 5, 6-membered ring. And between those, the 6-membered ring is preferred. And so it's one way of kind of controlling the chaos is like 8-member rings are not as stable as the 6-membered rings. And so we are mostly going to get this 6-membered ring product and not get as much of the 8-membered ring product. Same thing for the other ones. I'll let you kind of like explore, but it's like the inside versus the outside. You'll get either a 5 or 6-membered ring, or you'll get something bigger. And the 5 or 6-membered rings are preferred. Oh. A 4-membered ring is not happy. 4-membered ring wants to explode. So yes, to answer your question, yes, I'll say. Another thing our class does not get much into, but you might see on the MCAT, which is why I just want to like flag it. So a really classic base that's sometimes used in enolate chemistry is called LDA, lithium diisopropyl amide. So it's a nitrogen with a negative charge, which is very basic. But what you can do is you could use a base to make entirely your enolate, and then you could dropwise add in what you want to be the electrophile. And if you dropwise add in the electrophile, then this doesn't have the chance to get turned into an enolate itself. We know that this is going to be the thing that's attacked. But this is something that's covered a lot more in like other classes. Like for a class that would spend like 2.5 weeks on enolates, then they would go into stuff like this. But we don't cover it as much. But big idea, there's a lot of chaos. We need ways of controlling it. Last up, we have the other enolate reactions. So our big boy enolate reactions are the aldol, where the enolate attacks what? Ketone or aldehyde. And the claisen, where the enolate attacks what? Ester. Thank you. So enolates can also attack other things. So an enolate could attack an enone here. And if the enolate attacks the enone, you do 1,4 addition. And so what you get as your product is a 1,5 dicarbonyl, which kind of feels weird, but it's just the product. Oh, that was not what I meant to circle. I meant to circle this. 1, 2, 3, 4, 5. So if you have a product with 2 carbonyls that are 5 away from each other, you did a Michael addition. So you need to be disconnecting between the 1, 2, 3 position, which is going to be the end of your enone, and then 4, 5. For this, typically what we use as a nucleophile is a dicarbonyl, just because it's more acidic. And it's more of a driving force for the reaction. You'll also, for this one, have an annoying step, because you'll still have a dicarbonyl in the product, and it'll still be acidic. But that's kind of one option for other things enolates can do. They can attack an enone. Enolates can also just do an SN2 attack. So like straight up, enolate can go and do a backside attack, and we've done an alkylation on our enolate. Now, this is one that I have seen in synthesis and line problems in the past. I don't know that it does on the final exam, but this is an example of something where it's simple enough. We're not doing full aldol claisen things where like a lot of different options can happen. So an alkylation, I think, would be fair game to see on like one box problem or one little part of a synthesis. You said, we'll see. We'll see. Last one, I think, is one of the cool ones, is decarboxylation. So with decarboxylation, you start off with a beta dicarbonyl. So this could be the product of what reaction? Beta dicarbonyl. The Claisen. Good. So we could do a Claisen reaction, and then we could do this, where we could do first a hydrolysis of the ester, and acid work, I've got it to an acid. And then we do this cool 6-membered ring transition state, where our double bond can grab the H, the electrons can fold down, make a CO double bond, and then we can break this sigma bond, and poof, we've kicked off a CO2. And with this, we removed a carboxylate, so it's a decarboxylation, removing CO2, which, I don't know, I just think she's neat. The very, very, very last reaction is the monic, which is kind of like a very meta reaction because it's more of a reaction scheme than anything else. So this is like our game plan map of what is happening in the monic reaction. You have an amine and an aldehyde typically that are going to come together and form an iminium. That's lecture 5 that you've seen. And then you have a ketone, which is going to do a tautomerization that we saw in this lecture and become an enol. We're not going to form an enolate because we're at pH of about 5, so slightly acidic. We're not going to have like a strong base. So we are just working with enols. And then the key thing is our enol is going to go and attack our iminium. And that is the one thing that's kind of new about this reaction scheme. Everything else is kind of putting together pieces that we saw from lecture 5 or earlier in lecture 10. And what we get here is a beta aminocarbonyl. So it's kind of like our aldol, but the nitrogen version of it. With this, it's almost guaranteed to be a like final exam mechanism question. Like it's most years we do a monic reaction, mostly just because it's a great way to test both lecture 5 stuff and lecture 10 stuff. And then also it just looks kind of crazy, y'all. So practicing like seeing it and watching out for it, I think is going to be big. But let's look at this one from the problem set, challenge problem number 6. So with this, let's try to find our functional groups. Do we have an amine present? Yeah, we have our amine. We have pH around 5. Do we have an aldehyde? We do. But then do we have a carbonyl, like a ketone that could be our nucleophile? Not yet. Not that I see. But we know for the monic we could do our imine formation. And when we connect to these, like we would do something like this. We would make a 1, 2, 3, 4, 5-membered ring with a nitrogen. And the product with the whole imine is going to be there. It's a bit of a beast to draw. I'm sorry about that. So this is our imine girl that we could form. But then the big thing is, this is the point where we would want an enol to attack, right? And we don't have an enol. But we see the bond that needs to form. We know that a bond needs to form here. So is there anything that's related to this carbon that's kind of like an enol? If we want the bond to form here, based on our product, well, who is she? She is Miss enamine from lecture 5. And we said at the very beginning, enamine is like the weird cousin of the enols and enolates. So she can do the exact same attack of pushing in, and the alpha carbon goes and attacks. And then that is going to lead you to this product after some like neutralization steps. Actually, does it do it directly? Oh no, we would have to do one more step where essentially we'll have this with a positive charge on it, like NH+, and then we'll need to do an alpha deprotonation again. But that's kind of the crux of it. And again, the hardest part of this was just seeing what had happened. I'll probably not do this skill builder with y'all just to save time so that we can end closer to the real time. But the biggest piece of advice for lecture 10 is this box. Make flashcards of these, get to where you can spot them really, really easily, because these characteristic products let you know what happened. So for the aldol addition and condensation, it's the enone and the aldol. For the Claisins, the dicarbonyl, a beta dicarbonyl, I should say. For the Michael, it's the 1,5-dicarbonyl. For alkylation, you've added an alkyl group at the alpha position. For decarboxylation, you have poofed away a carbon. And then for the monic, it is the beta aminocarbonyl. But I think that's all I have for you. This was our last section. Oh my gosh. Wow, I'm so sorry. I'm so sorry. There are no more sections. But thank you for coming today. I really appreciate it. And get some rest this weekend, too.